Hi, and welcome back, everybody. Continuing chapter 9, we are now at the point where last chapter we had defined kinetic energy, and we had just gotten done just now defining potential energy. Now what we're going to do is we're going to combine them into a statement that we call the conservation of energy. All right, so if we have an object that only is acted upon by conservative forces, that is, forces that don't lose any energy as they change from one form to another, we can combine these two theorems. Now part of this got messed up a little bit. This is from last chapter, the work kinetic energy theorem, all right? And we said that the total work that is done is equal to the change in kinetic energy, all right? Final minus initial. This is the part that got mixed up. This chapter right here, definition of potential energy, that got skipped to the next line right there, that's this. We said that for conservative work to be done, it results in a negative change in potential energy. That is, U initial minus U final. Our K, our kinetic energy, is change is always that's not the U, it's K. Final minus initial. K final minus K initial. All right, well, both of these are statements for work. Total work that is done by a conservative force, work that is done by a conservative force. So we can say, all right, well, since those two are the same thing, we then can say these two statements about kinetic energy and change in potential energy are also equal to each other. All right, so this is our combined statement now, and this is our statement about conservation of energy. As kinetic energy changes, we can say that potential energy changes inversely. All right, the more, so you have something at the top of a hill. It's got a lot of potential energy and no kinetic energy. As it starts to roll down the hill and gain kinetic energy, it loses potential energy. All right, so the increase in kinetic energy is equal to the decrease in potential energy, and so forth, and vice versa, I should say. All right. So, really, this is our. Do I have red here? No, here's red. All right, so our change in kinetic energy here, or KE, I call it sometimes. And then we have, I think in blue, it was our negative change in potential energy. U, or if you want to call it PE, that's fine too. If we expand them out, we have our final kinetic minus our initial kinetic, being equal to our initial potential minus our final potential. So let's just take all of our finals and our initials and move them all to the same side. So we're going to add this, I'm going to, well, everything's going to be minus right here. I'm going to bring this over to that side. I'm going to take my final kinetic energy and bring it over to here. And if I undo all the minuses, this is what I finally get. All right, we just rearrange that algebraically. So we have all of our initials and all of our finals. So that means let's say you've got a lot of potential energy at the beginning, all right, and no kinetic energy at the beginning. Well, at the very end, maybe it's all kinetic energy and it's no potential energy. That means like maybe it rolled down the hill and it has no more potential now. So the point here is that the energy that exists beforehand and afterwards is going to be the same, the sum of the two. If it's partly rolling down the hill, there's probably still some potential and some kinetic left. And which means it's got some kinetic energy and some potential left as well. So what we can do to simplify this even further is to make it into a statement like this. The total energy in a system at any one point, we call that the mechanical energy, all right, as opposed to chemical energy and other kinds of energy. The mechanical energy, the ability to do work, can be described at any one point as being just E. All right, so it's the sum of those two energies, our potential energy right here and our kinetic energy. I have the wrong color, don't I? I think my potential was blue. Our potential energy in blue and our kinetic energy being in red right here. All right, those two summed up equals E at any one point, whether it's initial or it could be final or it could be anything in between. All right, at any one point you say. That's what the energy is. It's the sum of those two different kinds of energy. And so since energy, if we're assuming here that energy is not lost, that it is conserved, we're going to say that the energy of the system, the sum of these two, initially has to equal the energy of the system finally. It might be a different sum of these two, but the sum still has to add up to the same amount of energy as it had going into the system. All right, the energy is conserved. It's the same going in as going out. So we're going to apply this to one example right here, example 9.6, and we'll probably do 9.7 and 9.8 together in class or possibly in a different video. But we're going to do 9.6 together and kind of lay this out and make application of this, okay? So here's going to be a welcome sight to many of you, hopefully in the near future, graduation. And so as you probably know, at graduation, you throw your hat up in the air. All right, so what we're going to do is we're going to make statements about the energy of this hat as it's leaving his hand and as it's at some point up in the air. All right, so let's just read over this and see if we can make some sense out of this. At the end of a graduation ceremony, we've got a 0.120 kilogram hat, all right, or mortarboard or graduation cap, thrown up in the air with an initial speed of 7.85 meters per second. All right. So, an initial speed right here, that means which kind of energy involves speed? Well, that's kinetic energy, right? And by the way, I'm not going to stick to my color code because that's just going to take too long. I'm just going to stay with red. Our kinetic energy, initial right here, is defined by its initial speed. Okay? We also say that frictional forces can be ignored. That's good news because frictional forces are non-conservative forces. That means they take energy out of the system that you never get back. All right? So the question is, what is the speed of the cap when it is 1.8 meters above the release point? All right, so it has been displaced upwards, or the height is 1.18 meters. And so what is the speed of the cap? Well, we can figure that out, but we really probably do better to say, all right, well, what is the kinetic energy of the cap at this final point up here? All right, because speed is involved with kinetic energy. Okay, well, we can make a statement about kinetic energies of the system, but if we want to include all energies of the system, we need to account for the potential energies as well. All right, so, you know, I will go back to red and blue after all. So it has some kinetic energy here and some kinetic energy up here. But we need to include potential energy. So what is the potential energy initial right there? Well, the good news about potential energy is that you can put 0 wherever you want. So if we're saying, hey, let's assume this to be 0.0 right here, then we can say, all right, well, the initial potential energy is 0 joules. All right, well, we've got a potential energy final as well up here. And so that's going to be added with this. The initial potential energy is going to be added with that right there. And so if we know what our potential energy final is, we can include that in. So how do we find potential energy at any one point? Well, potential energy, as you'll recall, is mg times our height, h. Or I think in our notes we had mgy. It could be thought of as the same thing, but it's the displacement vertically. All right, well, we have that height right here. That's good news. So let's make a statement about the potential energy beforehand, that is initially, and finally, and see if we can solve for that final velocity that's wrapped up in the potential energy final right there. Okay. So now I really am going to stick with one color. I'll stick with green. Hopefully you can see it okay. All right, so we say that energy initial has to equal energy final, right? So we can say the kinetic energy, it's supposed to be initial right there, plus the potential energy initial has to be equal to the kinetic energy final plus the potential energy final right there. Well, part of the good news of this is the fact that that goes away right away because that's 0. And the speed that we're looking for, the final speed of this cap, when it's at this point right here, is wrapped up in that kinetic energy final right there. So let's just subtract this potential energy final over there. So we say K initial, or not plus, minus, right? Minus U final equals kinetic energy final. Okay? So we're still solving for speed, and speed or velocity is wrapped up in there. So let's expand all these out to our various different descriptions of kinetic energy and potential energy. And I can see very soon I'm going to have to change to a different color because green is going to get lost in there. I'm changing to black. Kinetic energy initial, 1/2 mv initial squared, right? Minus, what is our potential energy final? That's mg H, right? That's an H right there, not a L. H, okay, equals 1/2 mv final squared. Hey, that's great right there. The v final, that is actually what we want to solve for. So let's just rearrange everything and solve for the v final because we have everything else right here. I think the 2, well, what I'm going to do is I'm just going to multiply up the 2 in the denominator. I'm going to divide by the m right here. So v final, in fact, I'm just going to scratch all this. I'm going to make a little bit more room right here. I'll take this and just pinch all this down. So our working equation is going to look like this. V final squared equals, I'm going to multiply up the 2 and divide by the m. So 2 over m times 1/2 mv initial squared minus 2 over m times mg h. All right, well, let's simplify that a little bit because we're going to have some things that are going to cancel out, right? What's going to go away? Well, that 2 is going to go away, and that m is going to go away, and this m is going to go away right here. So that's going to make things a lot simpler for us. So our v final, in fact, let's just take care of that square as well. Let's take the square root away. Oops, I don't want to do that. And just put a square root over everything. It's going to be the square root of what? That's v initial squared because all this other stuff went away right there. Minus 2gh. That's a heck of a lot simpler. All right, so it's going to be the square root of, what's initial velocity squared? Well, it's 7.85 meters per second, that value squared, minus 2 times 9.81 meters per second squared, times our height, which is 1.18, and I thought I had enough space, 1.18 meters, so it's a square root of all that stuff right there. What do we get when we solve for our final velocity right there? I don't know about you, but I get 6.2 meters per second. It's probably still going up. And by the way, just a little tip for life right here. Mortarboards or graduation caps are square, and they spin around, and squares have edges. And so really, seriously, when you do this, keep your eyes on the skies because people have gotten corners of mortarboards whacked in their head. So tread lightly when you throw your graduation cap up in the air. But anyway, that's how we solve this. This right here is our assumption. All right, all the energy initial equals all the energy final. Break that into kinetic and potential initial, and kinetic and potential final, and you'll be in good shape. All right, so that's example 9.6. See me in class or look for other videos on 9.7 and 9.8, but we'll take care of those as they come, if they're going to be on the same principles. Thanks for following along. I'll see you on the next one.